Hello, and welcome to a previously recorded version of our MDSC e-training course. My name is Louis Wagsback, and I'll be the instructor for this course today. First off, I want to thank you for being a customer of TA Instruments. The fact that you're attending this course means that at some point, either you or someone else at your company has purchased equipment from us, and we're appreciative of that. This is one of a series of advanced courses designed to ensure that our customers get the maximum benefit out of their thermal analysis systems. Hopefully, before you take this course, you've ran the instrument, you've taken our DSC QuickStart course, the basics of running the equipment, and this is going to give you more information on getting the best data out of modular DSC. Now, because this is a previously recorded course, there's a couple things that I want to explain to you. One is to hear the audio for this recorded course, you must have a sound card for speakers. So obviously, if you're hearing me now, you've got that, so you're in good shape. Also, because it's a recorded course, there's not a live instructor to ask you questions on. But what you can do is email me questions. And at the end of this presentation, there's going to be an email address. And you can send an email to that address with questions. Now, at the bottom right-hand corner, you can see down here this says slide number 2. That is a slide number. This will be on every slide. And so what you can do is you can record that slide number and what your question is, and then you can email that question to us, and we will answer back. Now, next thing is in the bottom right-hand corner, typically when it first starts off, there's a WebEx player controls. Now, these controls allow you to rewind, fast-forward, resume listening to it. So you've got control of this. If there's something that you want to go back over, you can hit rewind and back it up and then replay it again. Okay? That's about it on the preliminaries. Let's get started now. This is the agenda that we're going to go through. We're going to go through a basic introduction of modulated DSC in this class. We're going to go through some theory of modulated DSC and how to calculate the signals, etc. Then we're going to go through calibration, how to calibrate the specifics that we need to do for modulated DSC. Then we'll go through experimental conditions and considerations, and then we'll talk about data interpretation lastly. Now, this course is designed for users of our Q100 and Q1000 DSCs equipped with modulated DSC. There's some screenshots. There's a lot of specifics that are for the Q series. Now, if you have a 2900 series, you may be able to pick up a few things out of this, but just bear in mind that this is specifically designed for Q series. The DSC QuickStart, or appropriate knowledge, is a prerequisite for this course. What we mean by that is that you ran the instrument for a period of time, you know how to get it through the software, you know the basics of DSC. Because I'm not going to explain all those little basics. Those were explained in the DSC QuickStart. And obviously, that you should have had the DSC installed and calibrated by one of our service engineers. That way you ran some basic DSC stuff, maybe even ran some modulated stuff, and then maybe this will make some more sense to you. After completing this course, you're going to have a basic understanding of modulated DSC. You're going to have the ability to calibrate your modulated DSC, an understanding of how experimental conditions affect your data, and how to run samples correctly and get the best results out of them, and a basic understanding of interpreting the modulated DSC data. Now, DSC, just what is DSC? Just as kind of a quick review, and kind of the lead us into the modulated DSC. DSC measures endothermic and exothermic transitions as a function of temperature. DSC has a wide variety of materials, polymers and pharmaceuticals probably being the most common, but also in the food and biological industry, organic chemicals and inorganics. The transitions that we measure with DSC are the glass transition, or TG, melting and crystallization, and then also curing and cure kinetics, onset of oxidation, and heat capacity. And heat capacity is going to be one that we're going to talk about also here in modulated DSC, in addition to glass transition, melting, and crystallization. Now, modulated DSC takes standard DSC, and it overlays a sinusoidal temperature oscillation on the standard or traditional temperature ramp. And we'll talk about what that gives us here in just a second. Let's go through some of the basic theory. Now, this equation here is the basic DSC heat flow equation. Okay? The first term here, dH/dt, that's our DSC heat flow. Okay? Now, that's in watts, typically maybe a milliwatt, and a watt is a joule per second. The next term is CP, is heat capacity, in joules per degree C, or it could be the sample-specific heat in joules per gram degree C times the sample length. So think of that. The heat capacity is the specific heat of the material times the weight of the sample. Okay. The next term here is our heating rate, D temperature, derivative of temperature with respect to time, right? That's our heating rate in degrees C per minute. And this last term is a kinetic term. This is heat flow. This is a function of time at an absolute temperature. And this is typically called joules per second. That's our heat flow, like our first heat flow term. This is our kinetic heat flow term, same units, joules per second, or a watt. Okay, now let's look at heat flow due to heat capacity. So this is a sample of polymethyl methacrylate, PMMA, and I've ran this experiment. So I took a sample and I heated it up at 10 degrees a minute. So that's this top curve. I cooled it down and I heated it up at 20 degrees a minute. And this was never taking it out of the cell. This is just heat up, cool down, heat up again. All right? Now, if I take a point someplace here in the baseline, and I chose 60 degrees, and I measure the heat flow there, so minus 2.235. If I go and double that heating rate, so go at 20 degrees a minute, I should see this double, right? And why do I say that? Remember the heat flow equation. We're not talking about any kinetic term. What we've got is heat capacity times heating rate. The heat capacity of the material is the same. The heating rate's doubled, so our heat flow should double, right? So, and that's roughly what we see here, minus 2.2, minus 4.4. So that was good. Now what happens after we make this 20 degree a minute run? What if we cool it down again, and I chose 5 each time, but if we cool it down again to room temperature or a little bit below, and heat it up again at 10 degrees a minute? We should see basically a light on top of that. And that's what we see here. So now I've got 3 different heating rates, or 3 heating rates, 3 runs plotted here. The first 2 are at 10 degrees a minute. There's a green curve and a blue curve that's overlaid here. You can see how well that lines up. If we look at the absolute value, the first time at 5 degrees a minute, it was minus 2.235. The second time, 10 degrees a minute. Second time at 10 degrees a minute was minus 2.24. So we're seeing basically the same value. And that is heat flow due to heat capacity. We can sit here and cycle this run in perpetual, forever. And we should not see that heat capacity change. We should not see the heat flow value change at that temperature. Okay? It's going to depend on the heating rate, obviously. But at the same heating rate, at the same temperature, we should get the same value. That's until we see a change in the structure of the material, that we either decompose the material, that the material crystallizes, if it's a semi-crystalline polymer, or a pharmaceutical that has some crystalline structure. We see a loss of volatiles. Something changes. That's the only time we'll see the heat flow change. Now, the kinetic heat flow. And this is an example, and probably a relatively easy way to think about kinetic heat flow is the isothermal cure of epoxy adhesive. Now, probably most of us have mixed up the little ribbon adhesive or the little adhesive in a syringe that you squeeze out and mix up, and you know that gives off heat, right? It's an exothermic reaction as it goes through the cross-linking and curing. This is an isothermal cure of a high-temperature set epoxy, and I've done it at 3 different temperatures. Or actually, we did. I didn't actually run this data, but so at 150 degrees, we see within a couple minutes that we see the peak occur here. We'll see it large, quickly gives off heat, and then goes back down to baseline. But if we drop 15 degrees to 135, we see that that doubles or so the time it takes to get to that peak. And we also see that that peak height is a lot smaller. It's spread out over longer time. And if we cool down even further to 121 degrees, we see that that peak temperature is not out to about 116 degrees, as opposed to about 4 degrees, or say between 2 and 3 degrees, and about 6 degrees. So dropping it even further spreads it out even further. So it's the heat flow value. If we wanted to look at a heat flow value here, it would depend on what temperature we're at, but it would also depend on what time we're at. Okay? Now in modulated DSC, we use two simultaneous heating rates. There's the average heating rate. This gives us total heat flow data. This is going to be equivalent to standard DSC at the same average heating rate. Now this is important because, as we've just seen, the heat flow data is going to depend on the heating rate, especially with something that's kinetic, right, or heat capacity transition, right? So if we go through and we do our regular DSC at 10 degrees a minute, but then we do a modulated DSC at an average heat flow of, say, 3 or 5 degrees a minute, we're going to see slight differences. So we need to make sure we're comparing that at the same average heating rate. The modulated heating rate, this purpose is to obtain heat capacity information at the same time as heat flow. And we're going to kind of go through this a little bit more here in a minute. Now what do we mean? Here we have our average and our modulated temperature. Now when we set up a run in a modulated DSC, we have a period, we have an amplitude, and we have a average heating rate. And we're going to kind of go through that. But in this case, here's our conditions. We're modulating plus or minus 0.42 degrees, so that's our amplitude, every 40 seconds, that's our period, and then we're ramping 4 degrees a minute up to 290. So this is our average heating rate. Now this conditions here, this plus or minus 0.42 every 40 seconds, you might look at that and say, why in the world would you use 0.42 instead of just 0.4 or something round? This is what we know as heat ISO conditions. And we're going to talk about this further, and there's an important reason of why we would want to use this and when we want to use it. But if we do that, and we plot out our temperature in green, so this is our average temperature, so this is going up, the slope of this line is going to be our 4 degrees a minute, okay? And here is our average modulated temperature. So this is what we're from the modulation. So we can see our modulation there. Okay? But notice here we never go up and then down. We come up and ISO. That's why we call this heat ISO. Okay? So we're never decreasing the temperature during the modulation. We're never actually adding any cooling to it. Now if we blow up a small section here, okay, and look at it here, this difference right here is our amplitude. Okay? So this difference from the average heat flow value to the average temperature value to the modulated temperature value, right here at the peak point, is going to be 0.42. That's our amplitude that we're seeing. Okay? Now, if we go and take the derivative of those two signals, now why would we going to take the derivative? If we take the derivative of temperature with respect to time, look at our units here, degrees C per minute. What is that? That's simply our heating rate, or our average heating rate. And if we plot that, lo and behold, there it is right at 4, what we programmed. We can also do that on our modulated temperature, so we take the derivative of that. And we see that we're going from approximately 8 down to approximately 0. But see, we never go below 0, where there's never any cooling. Okay? Now, in modulated DSC, there can be cooling, but there doesn't have to be. And there's sometimes that you want cooling, and sometimes that you don't want cooling. And we're going to talk about that coming up in our experimental considerations. The other thing I wanted to show here is the period. The period is from this point to this point. So this is one complete cycle. Okay? That's our period. So we've talked about the amplitude, the period, and the average heating rate, just how those are looked at. Now, from this information, we're going to create two new raw data signals, and there's going to be three primary heat flow signals that are calculated. Okay? These two new raw data signals are the modulated heating rate and the modulated heat flow. And we're going to talk about the heat flow signals coming up here in just the next couple slides. The modulated heating rate is the stimulus that we're putting onto the sample. The modulated heat flow is the response that the sample is giving us back. So you can think of this as something like, for instance, a DMA, where in a DMA or a rheometer, we're putting a stress onto the sample and we're measuring the strain. Or we could be putting a strain and measuring the stress. Okay? In this case, we're putting a modulated heating rate and we're measuring the modulated heat flow. Now let's take a look at the raw signals. And it's always important, and a lot of things here we're going to talk about later, but we will talk about this later. It's important to be able to look at these raw signals. Sometimes this gives you a warm fuzzy about the data, and make sure that you, when you look at the data, you know that the data is correct. But the green up here is our modulated heat flow data. The blue is our modulated heating rate. So this is our stimulus, this is our response. Okay? Now you can see in this case, we're not going down below zero. And the only real exception is right here in the middle of the melt, and we kind of lose it just a little bit. And we'll talk about that as we go into the interpretation of data. If we look at our modulated heat flow data, look here, if we draw along the bottom here, here's our glass transition, right? There's our step change. There's a peak upwards. Sorry. There's a peak downwards, right? So we can see in the raw data all the transitions that we're really interested in here. Now this is a Quidge-cooled PET sample, and we're going to go through this sample in detail here. We're going to show different ways, different signals, and then in the end we're going to go interpretation of what's going on here. Okay? Now, let's go through, before we do all that, let's go through calculating the T0 modulated DSC signals. Now, some of you may have had our 2920 or 2910 with modulated DSC. And we calculate the signals slightly different now on the T0, on the Q series DSC, than we did on the 2920. Now, some of it is going to be similar, but there's a few extra steps that are using. Now, these next slides that talk about calculating this, these are not things that you have to do. Obviously, the software does this for you. The instrument does it. But I wanted to show how we get from where we start with to where we end up, okay? All right, the T0 DSC, if you remember the basics of what the T0 DSC does, it gives an independent sample and reference heat flow and temperature signals. So we can look at the reference side by itself, we can look at the sample side by itself. Because of that, we can deconvolute the sample and reference heat flow separately. So we can look at just the sample heat flow, and we can look at just the reference heat flow. And there's some benefits to that. And one of the benefits is shorter periods, and we're going to kind of go through that a little bit later too. But for instance, on the 2900 series modulated DSC, we normally didn't recommend going down below 60 seconds. But with the Q100, using the T4 heat flow, using that four-term heat flow equation, we can now go down to about 40 seconds and get very good results. With the Q1000, using T4P, so we're also using the pan mass and the resistance of the pan as it sits on the sensor and the reaction of the purge gas with that, we can now go down to 20 seconds, 30 seconds, but 20 seconds we've got good data on before. So that's going to be things that we can talk about later. Now let's look at some of these calculation flow diagrams. Now, first off, we're going to start off with the sample side, and we're going to calculate total heat flow and heat capacity. Okay? Now, first off, we take the sample modulated heat flow, the average value of that, to get our sample apparent total heat flow. We take the sample pan temperature. Now this is if we have a Q1000, because we're using the contact resistance to calculate the temperature. If we have a Q100, then we're using the sensor temperature. We take the derivative of that to calculate the sample heating rate. Okay? We divide heating rate into heat flow to get our sample apparent heat capacity. Now why can we do this? Let's look at this is our original equation that we showed earlier. We're going to refer to this several times today. So here's our heat flow, heat capacity times heating rate plus kinetic, right? Well, for now, forget about the kinetic term. We're not going to deal with the kinetic term right now. We're just going to talk about heat capacity, right? So if we take our heat flow divided by our heating rate, that's going to give us heat capacity. So here's heat flow, here's heating rate. So that's how we calculate the sample apparent total heat capacity. For the reference side, we do a similar thing, but there's an extra step. We get the reference modulated heat flow, take the average value for the reference apparent total heat flow, the temperature to get the reference heating rate. Now the extra step is the pan mass correction. Now this would be for a Q1000. For a Q100 you wouldn't have this, obviously. But the pan mass correction goes in place here, so we get the reference total heat flow. We take that number divided by the heating rate to get our reference total heat capacity, just like we saw on the sample side. Now what happens? We take the sample total heat capacity and the reference total heat capacity. We take the difference of those, delta, to get the total heat flow. But we take the difference, multiply it by our heat capacity calibration constant that we're going to talk about in the next section. That gives us our total heat capacity. We multiply the total heat capacity by the negative of the heating rate to get total heat flow. Now, this is several steps and several diagrams to show you how we get there. And it's slightly different than what we used to do in the 2900 series, and the reason is because we can look at that heat flow separately on the sample side and the reference side that we never could before. And this gives us a better determination, and that it's less frequency or less period dependent. And once again, you really don't have to worry about this. You don't have to go through all this. I'm just trying to show you how we get that. Okay? So this is how we get total heat capacity and total heat flow. Now let's look at reversing heat capacity and reversing heat flow. Okay. Now, reversing heat capacity is the same as what we used to call complex heat capacity on the 2900 series. Okay, just so we have the term straight. Now, we take, on the sample side, we take the sample modulated heat flow, we take the sample pan modulated heating rate. Once again, that's pan for a Q1000, that's sensor for a Q100. We use the ratio of those amplitudes to get the sample apparent reversing heat capacity. Say that 3 times quick. Okay? Now, why can we do that? Let's talk about standard DSC for a second and the way we measure heat capacity. So in a standard DSC experiment, heat capacity is going to be equal to our calibration constant times the heat flow of the sample minus the heat flow of an empty pan. That way we get an absolute value of the heat flow, divided by the heating rate times the weight of the sample. So that's the standard method that we would use to determine heat capacity with a standard DSC, non-modulated, non-Q1000 direct CP, etc. Now, an alternate way to do this, remember our PMMA data, where I showed at 10 degrees a minute we saw one value of heat flow. At 20 degrees a minute we saw a doubling of that. So we could look at heat capacity is equal to our constant times the heat flow at our second heating rate 2, minus the heat flow at heating rate 1. So it's differential between these two heat flows, divided by this difference in the heating rate times the weight. Well, that's what we just said on this previous page. We had the ratio of the heat flow divided by the ratio of the heating rate. Now think of this as our modulated experiment where we are modulating here. So we're seeing these two heat flows because as we modulated up and down between these two heating rates. So that's an alternate way to look at heat capacity, and that's how we're doing it here. And this is just to remind you of the example of the PMMA, where if we had, think of this as a modulated, where if we heated at 10 degrees a minute, heated at 20 degrees a minute, heated at 10 degrees a minute, heated at 20 degrees a minute, heated at 10 degrees a minute, and if we set that up in just a sinusoidal consistent modulation, we would see that data in between there. Okay? Now, reversing heat flow and heat capacity continued now. Let's look at the reference side. So we do basically the same thing that we saw before. This ratio of the amplitude there divided by the ratio of the amplitude on the heating rate of the pan if it's Q1000, the sensor if it's Q100. That gives us our reference apparent reversing heat capacity. We use our pan mass correction again to get our reference reversing heat capacity. Once again, we take the difference times our heat capacity cell constant, our KCP reversing. There's two KCPs that we're going to talk about in the next section. That gives us our reversing heat capacity. We multiply this times the negative of the heating rate to get reversing heat flow. So now we've got total heat capacity, total heat flow, reversing heat capacity, reversing heat flow. The other signal that we normally might look at is non-reversing heat flow. Well, that's kind of the easiest one. Non-reversing heat flow is going to be total heat flow minus reversing heat flow. And once again, we get that from our original equation that we looked at. This is total heat flow, this is reversing, and this is non-reversing. Now, think of reversing and non-reversing as the reversing term is our heat capacity term. The non-reversing term is our kinetic term. Now, when we first came out with modulated DSC in the early 90s, we coined the term reversing and non-reversing. And in some ways, it probably wasn't the best term that we could have come up with, because it brings up the question of reversible and irreversible thermodynamically, and that's not what we're talking about here. What we're talking about, the reversing curve, is going to be a heat capacity component. This is what follows the modulation during our experiment. So depending on how fast we're going in that modulation, or how big a temperature range, we may see something that follows that or that doesn't follow it, depending on as we change those conditions. So you can actually see things move from the reversing to the non-reversing curve. But anytime we say reversing curve, think of heat capacity. Non-reversing curve, think of kinetic. Okay, so here's our basic modulated DSC heat flows and signals, right? Total, reversing, and non-reversing. Let's look and see what type of transitions go into each one. Let's first look at reversing. Now, what did I say reversing was? Heat capacity component, right? So guess what? One of the first things we're going to see there, that's our heat capacity. Kind of makes sense. Now, the glass transition is also going to show up there, because the glass transition is a step change in the heat capacity. Shows up in the reversing transition. And most of melting shows up in the reversing transition. Sometimes you will see reversing that is in the you will see melting that is in the non-reversing transition. But we will kind of go through this in a little bit here. Non-reversing transitions. You can see there's a lot of things that come into non-reversing. Enthalpic recovery. Now this is that little peak, endothermic peak that occurs at the glass transition. That would tend to show up in the non-reversing curve. Evaporation or volatilization. You have water coming off, have a solvent coming off. If the material crystallizes, that crystallization, that's a non-reversing. That's going to show up in that curve. If a material goes through a thermoset curing, that would be non-reversing. Protein denaturation or starch gelatinization, Those are all non-reversing transitions. Decomposition, and then some melting. Now what it turns out is that typically, especially in polymers, what we see is non-reversing melting means that it's very large, quote-unquote, perfect crystals, okay? So the larger, the thicker, the more laminar-type crystals tend to be non-reversing melting, where any smaller crystals tend to show up in the reversing curve. Now, in order to properly interpret modulated DSC results, it's important to understand what we're measuring in modulated DSC. Modulated DSC does not require heating and cooling to make a measurement. It does require a periodic change in the heating rate. That's all it requires. Now, we're doing this in a sinusoidal manner, but you could do it in several different ways. But that's what we've done. Modulated DSC does not measure the reversibility or non-reversibility or irreversibility of transitions. Modulated DSC does measure how much the heat flow changes, the heat flow amplitude, for a controlled change in the heating rate, or the heating rate amplitude. And then modulated DSC does measure the average value of the modulated heat flow to calculate a signal that's equivalent to standard DSC, remember, at the same heating rate, same average heating rate. Now, once again, when we first came out with modulated DSC, there were some misnomers, there was some misunderstanding. Initially, people thought you had to have heating and cooling, but you don't. You just need that periodic change. When and why would you want to run modulated DSC? Now, I've had customers say, well, I've got a modulated DSC, so should I just run that for everything? And my answer is no. I would always run a standard DSC first, average maybe 10 degrees a minute. And the reason is because, let's look at a couple different ways. First off, if we're looking for a glass transition. If the glass transition is detectable and you can routinely analyze it with standard DSC, there's no other transitions that are masked on it. You heat it up, cool it down, reheat it, the glass transition's there, you can see it, it's easy to look at. Then you don't need to use modulated DSC if you're just looking for that glass transition. Because at 10 degrees a minute, you're going to see that faster than what you're going to see in a typical modulated experiment. However, if the glass transition is hard to detect, maybe it's really broad or very small, there's an enthalpic recovery or something else going on at the same time, then modulated DSC will make that a lot easier to find, give you more sensitivity to it, plus to separate out those other transitions. If you're looking at melting and crystallization, if the melting process looks normal, by that I mean just a single endothermic peak, nothing else going on, there's no apparent crystallization of the sample as it's heated, then you don't really need to use modulated DSC. However, if the melt is not straightforward, or if it's difficult to determine if crystallization occurring as the sample is heated, you can use modulated DSC to help interpret that. And we're going to show examples of that coming up here. And it turns out with a lot of polymers, there's a lot of stuff going on during the melt, especially a lot of the typical semi-crystalline polymers that we run. If you want heat capacity, modulated DSC is an extremely easy and convenient way to get heat capacity, because heat capacity is now a signal. Now remember how we talked about determining heat capacity on regular DSC? And there's basically 3 experiments that are required, and they use relatively high heating rates, 10 degrees or more a minute. And I say relatively high because depending on the sample, you may have a thermal lag to it, and that can affect it. Modulated DSC, you can get slower heating rates and get that data. But the 3 experiments, you have to run a baseline. You have to run a reference like a sapphire to calculate your heat capacity cell constant, the KCP, and then you have to run your sample. That's to get heat capacity by normal DSC. Now Q1000 is a little bit of an exception because we have what's called direct heat capacity on that. So if you have a Q1000 and you just want heat capacity, you can get that off of Q1000 easy enough. But if you have a Q100 or any other DSC, modulated DSC will give you that data. information, the heat capacity information, even easier. All right, now let's talk about calibration. First off, you have to calibrate your DSC as normal. So for a Q100 or a Q1000, you have to do a T0 calibration. You also have to do cell constant and temperature calibration. Now that has to be done. We went over that in the original QuickStart course for DSC, so everybody should know how to do that. Now what you need to do is to calculate the heat capacity constant. There's two of them. One's a total heat capacity cell constant. One is a reversing heat capacity cell constant. And we're going to go through the steps here, but you may have to set the existing constants to 1, and I'm going to show you how to do that, and then have to run a sapphire sample. Now this is the instrument control screen, experimental view, and if you go to calibrate and cell temperature table, we get this window here. And see, we've got the total CP constant and the reversing CP constant. Those have to be set at 1. If you don't do that, then basically you're already correcting it, and if it's not giving you the right answer, you're going to put an additional correction. All right, now we have to run the sapphire sample. Before we go talk about running the sapphire sample, let's give a couple general things about calibration. First off, the heat capacity calibration is independent of heating rate, from 0 to 5 degrees a minute. Normally, you're not going to want to be doing heat capacity at a higher temperature than a heating rate than that. The heat capacity calibration is independent of amplitude, from 0 to 1 degrees C. The heat capacity calibration is dependent on the period and the purge gas that you're using. So you want to calibrate with what period that you're going to use for subsequent runs. So if you're using an 80-second period to make your heat capacity measurements, you want to use an 80-second period to do your calibration. Pretty obvious, right? And whatever purge gas you're going to use on your subsequent runs is what you want to use, because this will affect it, whether it's helium or whether it's nitrogen. Those are probably the two most common. Back in the software, if we go under our procedures, our summary procedure page, okay? So right now, we're going to have to do it in modulated mode, and we want to do a conventional DSC test, MDSC test. This is how we'd run the sapphire sample. Now, what we want to do is we want to go in and set an amplitude of, now these are some typical conditions. Amplitude of plus or minus 0.1. A range might be, say, 0.75 to 0.1. Typical range. And we're going to talk about some experimental conditions for measuring heat capacity later. But this is what I used for this one. Modulation period of 80 seconds. Ramp rate of about 3 degrees a minute, and I'm going to do a range from 0 to 300. Okay? Now once I do that and plot it out in the software, this is what I see. So I plot out heat capacity, which is our green line here, and reversing heat capacity, which is a blue line. And we want to plot it versus temperature. Now we can go and look at that in the data table. And if we do that, we can go to View, Data Table. I'm going to do it as a spreadsheet. Now, hopefully most of you have taken the Universal Analysis QuickStart course, and it'll show you how to do all this. But to do it as a spreadsheet, you have to have Excel on your computer that you're doing this on. Otherwise, you could do it as a report. But I'm going to do it on the spreadsheet, and this is what we get. So we're getting a plot of temperature and the two heat capacity measurements. Now notice I did it at 26.85 and every 10 degrees after that. Now that looks like it's probably, it's kind of a weird temperature. Why would you pick that? You'll see in just 1 second here. Now this is that table again. Okay. And to calculate the heat capacity calibration constant, K, we have to look at the ratio of the theoretical heat capacity versus the measured heat capacity. And measured is what we got here in this table at each temperature. Now, where do we get the theoretical? We can get it in off the software and in the instrument. But this is the table that you would get from our software. And you can see down here at low temperatures it's minus 143.15, blah, 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 blah. But once we get above zero, it's 6.85 degrees, and every 10 degrees after that. So that's why I did that when I look at my data table. And then here's also, just for your information, is the reference of where we get this information from. It's ASTM 1269. Now, to determine the heat capacity cell constant K, there's multiple ways that we can do it. One, we can do it at one temperature. One, we can do it at multiple temperatures. What I'm going to do right now is just first off do it at one temperature. So if I take, say, 106.85, and I get the value out of that table, 0.9168, I use this ratio of the theoretical, which is the literature value here, divided by the measured value for both the total and the reversing. So I get these numbers, 1.11 for total, 1.0382 for reversing. So that would be the number that I would plug in. But maybe I don't want to do it just at one temperature. Maybe I want to do it at multiple temperatures. So what I would do is I would get the literature value for each of these multiple temperatures. So in this case, I did it about every 50 degrees. Calculate the values at each of those temperatures. So get our KCP and the K reversing CP at each temperature. So at 56.85, I take this literature value divided by the measured value, and I get this number. And I do the same thing here for the reversing, and I get this number. And then I repeat that at the different temperatures. And then what I do is I calculate an average for each of those. So it shows our average value. And you can see it doesn't change a lot in this range, but it does change slightly. Now the total heat capacity is a little bit more. It changes a little bit more than the reversing heat capacity. Now what do we do once we calculate that number? We have to go back in the software. Now remember, we go to Calibrate, Cell Temperature Table, and here's our box here. So we put in those K values into the software, in the cell calibration table. So now we're done with calibration. Let's talk about experimental considerations. Just some general guidelines. Sample preparation, specifically on this slide, is sample weight. The sample to be analyzed must be representative of the total sample. Kind of sounds easy and common sense, but occasionally we have people that have a gallon can of material that's not mixed very well. And so as you take out samples, you get different results. So that's really not a very good sample to run on any analytical technique, but for instance on this modulated DSC or DSC. The change in heat flow due to the transition of interest should be in this range from 0.1 to 10 milliwatts. Now, what does that mean? For either metal or chemical melting, so let's say a pure material, maybe an organic chemical, pharmaceutical type material, you typically might want to use 5 milligrams or less. For polymer TG or polymer melting, somewhere approximately 10 milligrams. And for composites or blend, somewhere around 10 milligrams or greater, maybe 15 milligrams. Now, probably my typical sample size that I shoot for when I'm running most of the polymers that I run on modulated DSC is 10 milligrams plus or minus a half a milligram or so. That's kind of what I shoot for. And I tried it that way. If I'm comparing samples, I have samples that are approximately the same size. Sample shape. If you have a pellet, do you want to just stick that pellet in the pan and run it? No, you don't. You want the sample to be as thin as possible and cover as much of the bottom of the pan as possible. If you have a pellet, one thing I've seen people do over the years is take that in the sample press and smash it to flatten it. Is that something you want to do? The answer is no, you don't. It'd be a lot better to cut the sample rather than crush it. So what I would recommend is you take a razor blade and hold the sample with needle nose pliers or tweezers or something and slice out a cross-section out of that. Now, lids should be used with sample pans in order to keep the sample in contact with the bottom of the pan. We always recommend using lids, with the exceptions of, OITs and photo calorimetry experiments where you have to have an open pan. Otherwise, we always recommend having lids. But it's even probably more important with modulated DSC. Since we're putting a modulation onto there and we're heating it up and down at different rates, it may not be increasing and decreasing in temperature, but at least at different rates, we want to make sure that sample follows that. Here's just the different sample pans. If your sample is a solid, non-volatile material, I would definitely recommend using the standard sample pans like I showed here. Here's the bottom and the top. If it's hermetic, you use hermetic pan if the sample is a liquid or if the sample has volatiles in it, because volatiles coming off can change your results. Now this shows a standard pan that shows a good and a bad. Notice here we've got a nice flat bottom, where in here it shows up, you can see a ring there. So that sample's been over crimped. So when you go to crimp a standard pan, as you feel any type of resistance, you want to stop and you want to take the pan out and look at the bottom of the pan and look at the top of the pan. And you want the pan to just start crimping it. Just start. And so let me just make a crude drawing here, but if you have the lid like this and the pan like this, you want that pan just to be over so it holds that lid in place. You don't want to smash it a lot so that it flattens it and it makes the bottom be kind of ugly like this. Okay? To set up a run, obviously you have to be in modulated mode, and we kind of mentioned that earlier, but you would do that by using a little drop-down arrow here and pick modulated. The next thing we want to talk about is the signals to store, and that's using this icon that's highlighted here. Now this is a list of all the different signals that you can store on a Q-Series instrument in modulated mode. And you can see basically I've got them all with the exception of two things stored. And that is how I run the samples. That's what I would recommend doing. I always like to, I'm going to start at the bottom here, I always like to store the sample purge flow, because it's just a way that I can double check and make sure that, you know, that I've got a good flow rate and I've got the flow rate that I expect to. These raw signals like modulated temperature and modulated heat flow are important, and we're going to show some reasons that you would look at that data later. It's not a bad idea to store temperature amplitude and heat flow amplitude. You may want to look at that. And then these are probably the standard signals that you're going to be looking at, things like the heat capacity, non-reversing heat flow, reversing heat flow. These two that I have unchecked, heat flow phase angle and reference sine angle, those are those really do not come into play except during the middle of a first order transition like a melt or some energetic transition, whether it be endothermic or exothermic. And so what will happen is that would be to look at phase corrected signals. For those that have a DMA, when you put a stimulus onto a sample and measure a response, there's a lag in that, right? And depending on where you're at in the structure of the material, it may be in phase, it may be out of phase. In modulated DSC, typically we don't see that it becomes out of phase until in the middle of a transition like a melt. And normally we don't worry about that because we're not looking at the reversing and non-reversing independently or quantitatively independently. We're looking at them together. So this is why we recommend you do this. Now test mode. You can see a lot of different test modes. These last three down here are the typical ones for modulated DSC. Conventional modulated DSC, modulated DSC heat only, quasi-isothermal, and obviously you can go into custom and create your own. So let's talk about different samples that we might be looking at, or different characteristics of those samples is probably a better way to put it. If we're going to look for a glass transition, and we want to run modulated DSC, I would recommend using the conventional modulated DSC template. I would use an amplitude of somewhere between 0.5 to 1 degree. Typically, I use a period of 60 seconds. Now with the Q1000, the minimum usable period is 20 seconds, so you could go lower. But I find that I typically, or I get better data if I use like around a 60-second period. And that's normally what I use. Q100, the minimum usable period is 40 seconds. But once again, I usually make my measurements at 60. You want to use a heating rate such that you get 4 to 5 cycles over the transition. Depending on your transition, that could be very slow. That could be relatively quick, depending on your period. So if you're doing a 60-second period and you find that 3 degrees gives you those number of cycles, 4 to 5 cycles, what happens if you go to a 20-second period? Well, you can triple the heating rate, right? So instead of 3 degrees, you can maybe run 9 degrees a minute, maybe almost 10 degrees a minute. Now here shows glass transition, so we're looking at the heat flow curve, and we're looking at the modulated heat flow data. So we can see, now notice we see the step change here if we follow the bottom of this. There's our step change. But notice the number of cycles here that we're seeing. So we can see we've got quite a few cycles over that to quantify that transition. And that's what we need to get good deconvolution, is 4 to 5 cycles. Now, if we go to, and we pick conventional template, and we go to the procedure page, this is what it looks like. So here we would have 1, 60, maybe 3, and then a temperature range. Probably my typical, this would be a typical if I'm looking for a glass transition. I might even decrease this modulation amplitude down to 0.75, but probably this is where I'd start with. Usually use period of 60 seconds. Ramp rate is probably somewhere around 3 degrees a minute is the typical that I would use. Okay. Now let's say, what if we're looking for melting and/or crystallization? You would want to use the MDSC heat-only template. Now this template, it's described as heat-only, but it's really heat iso, so that we heat up and go isothermal for a second, but never go cooling. Okay? Once again, I would use a 60-second period, but here's just a reminder of what the minimums are. You want to use a heating rate so you get 4 to 5 cycles over the transition. Where over the transition? The width at half height. This is for a melt or crystallization. And then the template will calculate the amplitude for you. Now here shows a melt transition, and I've got the modulated heat flow signal overlaid. So what I did is I integrated this transition, and I chose width at half height. So it tells me it's over 13 degrees. So I could go in, depending on the period that I'm using and the heating rate, and calculate how many cycles I get. Or I could sit here and overlay this like this and count them. So here's where I started. So here's 1, 2, 3, 4. Basically, I've got 5 cycles there, right? So I said 4 to 5. I've got 5. I'm in good shape here to deconvolute this melt peak. Back to the experimental view and the procedure page, the MDSC heat-only template. Now notice here we put 60-second period, 3 degrees a minute heating rate. Here's our start temperature. Here's our final temperature. We never put an amplitude. When we put this and we click apply, it puts the amplitude into for us. So the amplitude in this, for these conditions of a 60-second period and a 3 degree a minute heating rate is 0.477. So this would be typical. Okay. Now what happens if we increase the heating rate? So if we go up to a heating rate of 5 and then hit apply, we get a larger amplitude. We can go to a larger amplitude and still keep in the heat iso conditions. Now those amplitudes, it's also in the online help, and it's in the manual, but this is the table here. Now the template that I just showed calculates it for you. But if you want to change conditions or you want to do custom methods, you can use this to calculate. So if we're going at a 1 degree a minute heating rate, we would use this amplitude if we're at a 60-second period. 2 degrees, we'd use this amplitude. What happens if we want 3 degrees? We'd take this amplitude plus this amplitude and add them together. So that's our 0.477. So the table is additive, as the note down here says. Now, heat capacity. If I'm going to measure heat capacity with modulated DSC, I would use the conventional MDSC template. I would use amplitudes of somewhere between 0.5 and 1 degrees. And then I'd use a period of 80 to 100 seconds. And just as a note, remember, you want to calibrate at the period of interest. So if you're going to be using a 100-second period and measuring heat capacity to get the best quantitative data, you should have calibrated at a 100-second period. And then I would use a slow heating rate, maybe somewhere 2 to 3 degrees a minute. So here's back to the experimental page, and we've got conventional MDSC. I chose an amplitude of 0.75, modulation in this case of 90 seconds, my heating rate of 2. So this is how I'm going to run this experiment. Okay, now let's go into the last topic, which is about data interpretation. Common signals that I would look at when I look at a modulated DSC run in universal analysis. I would look at heat flow. This is total heat flow. I would look at reversing heat flow, and I would look at non-reversing heat flow. I'd plot those versus temperature, and voila, I get this. So here's my 3 curves versus temperature. Now, when I look at this, there's a couple things that I like to do to the graph, and I'm going to show you that. The reason I'm going to show you that is, 1, because I'm giving the course, so I'll show you the way I like to look at it. But 2, there are some reasons for why I do this. Now, one of the things is, if we look at the axes here, we can see that they're not all the same scale. It's not a bad idea to have it on the same scale so that you make sure you're looking at things on an even footing. But also, I don't like the way all these curves overlap in this region. So the first thing I'm going to do is I'm going to go into rescale and common scale. So this puts everything on the same scaling. And then I'm going to go into manual scaling. And manual scaling is this little icon right here. But I'm going to go in and I'm going to keep that. So in this case, I've got from, I guess I've got 5 total on the axes, right? From -4 to 1 here, or, yeah, -3 to -2. So I'm going to go in and I'm going to put start and stops, and I'm going to keep the same scaling on all the axes. So I'm going to increase it a little bit. I'll go up here to 8.5, but then I make sure all of them are 8.5. Okay, so I mean from here to here, I'm keeping the same number for all 3 axes. But I'm going to stagger them and stack them. Now there is a way in the software to do that. Under rescale, there's a stack axis. I don't necessarily always like the way it picks axes for me, so I usually do it manually. When I do that, this is what I see. So I see this, and I've got all the curves on the same scaling, and I've got them layered so I don't have overlapping. And it's just easier for me to look at it. Okay? Now before I go in and explain what's happening with that data file, and that's our quench code PET sample, I'm going to go in and look at some of the raw signals. So if I go in into change signals, and that's this icon right here, and once again, I'm not really showing you all this stuff because you should have got this in the QuickStart class, but I'm going to look at modulated heat flow, and I'm going to look at the derivative of modulated temperature with respect to time, which is going to give me my modulated heating rate. Okay, so this is the raw signals. So this looks kind of familiar. We saw something look like this earlier. Now, remember, all the transitions are visible in the raw data signals. Also, this is a way to look and say, yeah, did I have the heat ISO conditions? Yes, I did. I'm going from 0 to 8 in this case for my modulated heating rate. One of the things I like to do is examine the sine wave. Let me go back for a second. So if you take a look at just blowing up, say the first couple minutes of the run, the first couple, 5-10 degrees or something. And okay, here I did about 15 degrees. But what I'm looking at is I'm looking at the modulated heating rate, and I'm looking at the modulated heat flow. And I'm looking to see that I'm seeing a sinusoidal wave, and that I'm seeing that it looks like I'm getting a nice sinusoidal wave. I'm not seeing something that looks like a double peak. I'm not seeing something that looks like a square peak. I'm not seeing something that looks like it's kind of skewed. Those things would tell me that I'm not under modulation control. I'm not controlling the data like I expected to. And maybe it's because I'm at the very bottom end of the range of this instrument. Maybe I have a too big a sample. Maybe I'm trying to go at too high an amplitude. But this is a good thing just to look at the data and say, okay, do I feel like the data is in good shape? The next thing I do is, or the next thing that I just want to point out here is if we look at the modulated heat flow data and the total heat flow data. Now remember earlier we said that this was, we went through how this was calculated. But in essence, it's going to be the average value here. Now there's some slight differences on the way we calculate it, but that's what that modulated, or that's the total heat flow data comes out to be. Now to interpret the modulated DSC results. If we look at this, now this is our total heat flow or our DSC heat flow from standard DSC. And if we look at this, where would melting begin? So if we were going to integrate this peak and say, where is it melting? We would probably say right around there it starts to melting. It starts melting. So that's where we'd pick our integration limits. If we look at our reversing curve, now we might say, boy, you know what? It starts melting way back here. So which one's right? Well, really, the reversing curve is what's showing us where it's really starting to melt. But we wouldn't know that if we didn't run a modulated DSC run. Now, we're going to get in a minute here why we see that. Why do we see it melting way back there in the reversing curve, but we don't see that in the total heat flow curve? So here we've got the total heat flow curve and the non-reversing curve. Okay. Now, one thing about the non-reversing curve. Now, remember, this was heat iso conditions. At a heating rate of 0, the heat flow due to heat capacity is going to also be 0, right? So that makes kind of sense here, because if this number goes to 0, this is going to go to 0. 0 times anything is 0, right? So all we have left is our kinetic term. So our heat flow is going to just come from the kinetic term. So any heat flow detected at a 0 heating rate must be due to the kinetic process in the sample. Now let's go back here for a second. Oh, actually, let's go on further. All right, now what I've got here is the modulated heat flow curve and the non-reversing curve. At what point is the heating rate 0? That's at the top of this curve, right? Because that's when basically we see this is at 0 for at least part of it. Now, if we can blow up this curve and look at this. But what's happening here is if we think of this non-reversing curve, see how it's overlaid with the top of the total heat flow curve? And it should be, because the non-reversing signal is our kinetic parameters, kinetic data. And the top of this curve, the blue curve, is where we're seeing kinetic data, right? Now if we blow that up, and if we draw a line at 0, everything above this line is going to be kinetic exothermic activity. Anything below that line is going to be kinetic endothermic activity. So what do we see happen? We heat up, and this peak here is a crystallization peak. We see it crystallize, and it comes back. But see, it never goes back down to 0. Right around this region, we're always seeing some exothermic activity. And that starts to build, and as we're getting up in this region, it gets even bigger, and then it drops down endothermic, and then we get back to a baseline. That's important to help interpret these results. Now I've got all three curves plotted here, the total, the reversing, and the non-reversing, and this is how we're going to interpret these. If we look first, here's our total heat flow curve, okay, the green. And we can say this sample, because we know about it, here's our glass transition, here's our cold crystallization, and here's our melt. But we can see a little bit more detail if we look at the reversing curve individually and the non-reversing curve individually. So once again, here's our glass transition. Now notice if we look real close right in here, that glass transition kind of goes down and back up. So there's a little bit of an enthalpic recovery there. Okay? As we go up in our reversing signal, which is the heat capacity signal, we see a little bit of a step change going up there, just a little bit of a bump in the data. And this is due to the cold crystallization that's going on that we see up here. But as that happens, it changes the heat capacity. So we see a small decrease in heat capacity due to that cold crystallization. And then right above that, so somewhere right around here, we see the sample start to melt. Okay? Now if we look at the non-reversing curve, we see a peak that occurs here. That's our enthalpic recovery. We see an exothermic peak here. This is our cold crystallization. Cold crystallization is crystallization of amorphous material. So it's amorphous because we've French cooled the sample. So it starts off 100% amorphous. As we start heating up and we get above the PG, we get additional mobility in the sample. Energy gets put into the sample, and it gets to the point where the crystal structure starts to align and crystallize. And that's this exothermic peak we see here. But as we heat up, remember what we saw when we blew it up, we see that it's continuing to crystallize. Why is that? This is called crystal perfection. Now what's happening is we have crystals melting here, and they're recrystallizing there. Melting here, recrystallizing there. And that continues until at some point all of these crystals finish crystallizing and then they all melt. And that's when we see the finish of this. Okay, let's look at a couple other dative examples. Now, I just showed you the PET, which is kind of relatively easy to explain. It's a file that we use a lot. Now I'm going to show you some data that's not so obvious, and it's not always so easy to explain. Now this was a panel, epoxy panel coating, and this was an epoxy material that was on a panel that was sent to us. We scraped it off and put it in the pan. This is a very small sample. It's about 2 milligrams. And when you run this by regular DSC, or if you look at the total heat flow modulated DSC, you see a big endotherm area down here, and then we basically don't see nothing. We run that with modulated DSC and look at the reversing curve, we see a nice step change in this reversing curve. Now that step change is only about 8 microwatts. It's a very small step. Now when we showed the customer that data, the customer was like, okay, well, you know, this was back in the early days of modulated DSC. The customer said, well, you've got this new technique and you show me glass transition that I can't see before, but, you know, how do I know it's really there and it's not just something your black box is creating? So a glass transition is reversible. Now we talked about earlier that when we say reversing curve, we're not saying thermodynamically reversible. However, a glass transition is thermodynamically reversible. So what we did here is we heated and cooled it. And we looked at heat capacity, so reversing heat capacity, versus the derivative of reversing heat capacity. And if we do that, we can see that we see the glass transition on both heating and cooling. And we can see in the derivative, we also see that. Okay. Now here's another sample, and this is a complicated example. This material is quenched xenoy. Now xenoy is a blend of polybutylene terephthalate, which is a similar in material characteristic as PET, or polyethylene terephthalate, with polycarbonate. Now this was DSC at 10 degrees a minute. And the question that we've got here is, how would you interpret this data? Well, I mean, the first thing you could say, okay, this looks like a melt. That's pretty safe. And this looks like an exotherm. That's pretty safe. But is this here, where's our baseline? So is this an endotherm there, maybe? And this is maybe another endotherm? Possibly. Or is this an endotherm followed by a little bit of an exotherm? Or is this a glass transition? It becomes difficult to see exactly what's going on with this sample. So obviously we ran it modulated. And if we blow this, if we look at just a small portion, we're not really looking at the melt here, but if we see our reversing curve, our total heat flow curve, and our non-reversing. Now what we see here is two step changes. That's our two glass transitions. One of the polybutylene terephthalate, one of the polycarbonate. But what happens after we go through the glass transition of the quenched PBT? Just like on the PET, we see cold crystallization. That's our exotherm that's occurring here. So we're seeing exotherm crystallization of amorphous material. Then we go through the glass transition of the polycarbonate. Well, what happens when we go through the glass transition of the polycarbonate? Does it cold crystallize? No, it doesn't. However, when we go through this glass transition, it gives, the first one here, of the PBT, it gives us additional mobility. But we still have the polycarbonate that's below its TG. So that's still limiting our mobility. So some of the material crystallizes here. As we go through this glass transition, additional material crystallizes. And that's what we see there. And then in the melt region, which we don't have blown up on this curve, we see the reorganization, crystal perfection that we showed on the PET sample. Here's another relatively complicated example. DSC of microspheres in a drug, a pharmaceutical sample. And this is DSC at 5 degrees a minute. And once again, how would you interpret this data? Now we ran modulated DSC, and we've got the total heat flow, and we've got the reversing heat flow. So this first peak here, that looks like it could have been a melt, possibly, we see now as a glass transition with enthalpic recovery. And the reason is because we see nice and clear this glass transition in the reversing curve. This here, this big broad endotherm, appears to be a loss of volatiles. And we did end up running a TGA to confirm that. And there is a loss of volatiles in that region. All of a sudden, we see this large exothermic peak. Now, with pharmaceutical materials, sometimes you'll get polymorphic phase transitions, where you'll have a material melt and recrystallize to another crystalline form. But that's not what's happening here, because we never see any melting in this reversing curve. So in the reversing curve, we see all the way up here to where we see the crystallization in the total heat flow. We never see any melting endotherm. So that means that this is crystallization of amorphous material. It's not polymorphism. It's not another polymorphic form forming. And then as we heat up further, then we see melting, recrystallizing, and remelting. And that's the polymorphs that are formed while heating. Now this data here, this was something a customer sent me. And he sent me this curve and said, can you explain what the hell is going on here? And I looked at his method first off, 50 degrees C, plus or minus 1 degree every 60 seconds, ramping 2. Okay, that's not bad, right? That's pretty good much fits that curve that we're there, that region that we talked about. And what he was really concerned with was the reversing curve. And look at this garbage here and this garbage here. Now this exothermic peak in this region, this was epoxy material, so this was curing. And this is uncured material, and it goes through a curing process. Now if you think about this, something I pointed out earlier will help us interpret this. Look at the scaling here. From 6 to -2, so that's a scaling of 8 milliwatts. Look at the scaling here. From minus 0.35 to minus 0.55. Wow, that's a very small scale, right? So that's like 0.2 milliwatts. Why don't we put these on the same scale and see what it looks like? There we go. At this point, anything we see on this reversing curve looks like nothing. So the point is, we were making a mountain out of a molehill. We were blowing up something to the point that we made it look bad when there was really nothing going on. Now, what was that causing that right there? Look right here, we see a very small peak. Wonder what causes that? Well, look at the temperature. It's right around 0. It's water. There was a little bit of moisture, and that moisture froze and melted, and that's why we see what we saw there. Okay? Now here's another example from a customer. Now look at this material. In the reversing curve, we see an exothermic peak. This is very unusual. We normally do not see exothermic peaks like that in the reversing curve. So once again, the question is why? Now in this case, it wasn't due to a change in the signal. It wasn't that we were really blowing that one up. But here what I plotted was modulated heat flow and total heat flow. And I wanted to look at the data. Now everything, okay, we're seeing nice modulations, except, wait a second, what's that right there? Looks like there's something there. Let's blow that up. And all of a sudden we see that we are not maintaining that modulation through this transition. There's an extremely endothermic transition that actually is interrupting with our modulation. Now this data was actually done on a 2920 with an LNCA. And so this doesn't have the cooling capability that a Q-series has. But it's still kind of pertinent data that if you really maxed out and went down to maybe minus 150 and ran something on the Q-series, you might see something similar. But the point is, we're not maintaining our modulation. If we're not having a good modulation, then the deconvolution is going to be wrong. So that's really what we're showing there. Okay, well, I hope this course was beneficial for you. Just real quickly, and most of you have seen this before, but watch our website for more online courses. There's a lot of courses that we're in the process of bringing out and putting on our website, and we think that they'll be beneficial for you. We also have our TA Instruments Theory and Application Training course. This is given every other month or so in Delaware. We teach modulated, for the year 2003, we're going to teach modulated 4 times throughout the year. So that this is a full day on the theory and applications of modulated DSC. And then we have full days on other techniques. On-site training. You can have myself or one of our other application specialists here at TA come into your lab and spend a day with you running your samples and your equipment. Could be more than a day. Now there is a charge for that. The charge for that is $1,500 a day plus expenses. But that's something that a lot of customers have taken us up on to get additional training. So typically it may be a day per technique, things like that. Other help that you can get as you go through is our applications hotline and our service hotline. Those numbers are shown here. You can email AnswerMan. Most of you guys have seen this, and I'm not really going to spend much time there. The one point I like to make is if you call the applications hotline and it goes to voicemail, that means that that person's answering someone else's call. So leave a message and they'll call you back. You can also call your sales and service representatives. Okay, lastly, thanks for attending. Now, I told you there's an email address. Here it is here, webex2@tans.com. So if you send any of your questions to this email address, I will get back to you and answer them best I can, and we'll go from there. Thank you very much, and good luck using your modulated DSC. And if there's anything I can do to help you, please let me know.